Everybody. Sorry about the early technical difficulties. So we have two presenters today, Eroma, Abeysinghe, and Eric Coulter will give the topics that Nancy sent out in the meeting invitation. So Nancy just completed the Boston Marathon and is recovering from the San Diego-like weather that they have in Boston. So she asked me to stand in. I'm not going to go through any introductions. I'll let the speakers do that themselves, and let's get started. Is Marcus recording?
Yep, it's recording.
Okay.
Hi, I hope everybody can hear me clearly.
Yep, you sound fine.
Okay, so I'm gonna share my screen. Okay, share my screen. Can everyone see my screen? I put my presentation on.
No, not yet.
I don't think we're seeing your screen. We're seeing someone else's. Hang on.
Yes, I can see it. If you go to view options, there's a choice of screens.
Interesting. Thank you for that.
I shared my screen. So still you can't see it?
We could see it now if we choose your screen under view options.
Oh,
Where are these view options?
On the top of the screen?
There is nothing on the top of my screen.
So maybe if the other person who's sharing their screen can unshare, that might be automatic then?
True. Air 13. Can you unshare your screen, please?
You also probably want to get out of projector mode, right? I mean, or at least for our view, Eroma, on your screen, we're seeing your talking notes and stuff as well. At least that's what I'm looking at.
oh.
Yeah.
So you probably want to do like, well, either projection mode or,
Let me check that first.
I mean, it's okay. We can see the slides also. I just get to see your notes. So as long as you didn't write anything offensive in your notes, it's okay.
Right.
It's probably okay, but I don't want to confuse with them. Let me try again. It should be okay now, I guess. Okay. Okay.
Yeah, I had to disconnect that other person. So now once you share your screen, everyone will see that by default.
Okay, now what do you see?
Your Zoom, and there we go with the slides, but it's the presenter mode again.
Okay. How is it now?
We
It's
see you now.
Oh. Do you still it in the platform or the same?
There, that looks good. Oh.
The presenter mode is okay. I mean, we can still see the slides. I mean, that's fine.
Yeah, it's just that it's not ready.
I mean, I've never seen presenter mode come up on my laptop, at least, unless I have a projector.
Okay,
Oh,
that looks good.
That looks good.
finally. Sorry, guys. I'll start without delay. So the presentation today is that I'm going to talk about my experience in related to 3 ECS projects that I worked as a consultant. And I'll touch upon the requirements we got from the PIs and what we implemented for their requirement, and also a little bit on how the gateway operations are going for those gateways at the moment. And so I am Eroma, and I'm part of the Science Gateways Research Center here at Indiana University. And I also work as an ECS consultant, and I also work as a consultant for SciGap Poster Gateway platform that here we actually are actively working on. So moving on. These particular 3 projects that I have selected to talk about today, they all, there are similarities in these. So all these PIs, they wanted to provide their software or the tool they have as a service to the gateways. So I believe few reasons for that is that all these 3 groups, they have an actively developing and updating code, and building this code and optimizing it in HPC to work is a challenge itself. And on the other hand, since these codes are better performed in HPCs like exceed resources, the actual end users may not even have the sufficient resources to run them. For example, one of the gateways that we are going to discuss, the direct code is best run when it's on GPU nodes. And another belief I would say is that a gateway would contribute to reach to a larger user base and also to build a community around that. So these were kind of like the common ideas and facts around these gateways. So moving into looking at one of them, so the direct gateway, as the name says, it is to provide the direct tool, and which is developed and distributed by Danko Labs at Cornell. What they do is that that application predicts the locations or the regions which would regulate transcriptions of DNA into RNA. So basically, it will help with genetic basis, diseases, and things like that. And currently, they have pre-trained models that work on mammalian organisms, and they're going to bring up the rest of it as soon. So that's what they do, kind of. So what did they really require from the ECS project? So their requirement was that, the team was, the PI is Professor Charles Danko, and Dr. Zhong Wang also worked with the project, in the project with us. And what they wanted was, they wanted to provide, so they had their tool compiled and optimized to run on exceed resources, Comet and Bridges on their GPU nodes. And they wanted to provide this tool as a service to the users through a gateway. And another aspect they were concerned about is the large input files they have for this application. So they wanted to have a storage that would hold the input files and also the output files that the application would generate for users. So once these application outputs are generated, visualization was a key aspect for them, and they integrating a visualization tool, in this case, a genome browser, was also in place. After discussing all that, then we came to point how they want to provide access to their gateway. So they want users to create their accounts, like have them authenticated and authorized. But what they didn't want to do is they didn't want each and every account to go through a gateway administrator's approval process. Whoever who creates the account and get access should be able to directly use the gateway. So these were their main requirements. And implementing these requirements, so first what we did was, so we have a default gateway client that we would provide. So the gateway team provided that, and they hosted it in the Jetstream VM which has attached large volumes, so the data storage would not be an issue. And then in this particular project, ECS project, the PI's team and the gateway team, they work together in bringing all the gateway code changes and gateway theme changes and integrating their visualization tools into the system gateway. And so we used open source identity management Keycloak for the gateway user management. And one other thing is that since they were kind of concerned about file uploads, they wanted to have resumable file uploads, and we use TUS to support that resumable file upload. So any interference would not be an issue when it comes to uploading the files. So this particular gateway, one other thing is that so this is a completed ECS project. So up until this project or this gateway project came through, everybody else were kind of using the default gateway interface we would provide. But when it comes to direct group, they wanted to do some changes, some customizations in the group, in the gateway code. So they did that with us, and now currently this gateway is in production, and it's slowly but steadily getting users on board to work with. So moving to the next gateway that I would want to discuss.
Should we save our question for later?
No, go ahead, Mona.
I was just wondering how big of a data sets they're transferring using this TUS mechanism.
So the data sets were, I would say, a couple of GBs, couple of gigabytes, about hundreds of megabytes. But I remember large ones. Yes, not like maybe 4 to 5 GB each kind of a thing.
Okay, thank you.
Mona, you might be interested that Terry Schwartz, I think, implemented the TUS interface for Cypress.
Okay, thank you.
I think we're using that code that she contributed. Maybe not. It might have Java. Yeah, I think.
Shall we move on? Anybody else? Okay. So the other gateways, so the gateways have similarities, but this gateway is for the SymVascular group at Stanford, and Professor Alison Marsden is the PI of this project, and Professor Nathan Wilson also worked there. He's also working with us. So this is actually a currently ongoing project. So what they have is they have an open source software suite, which would do image-based cardiovascular modeling and then simulation. So the gateway is used to use this solver for blood flow simulations and analysis for its users. So why I selected this project was to talk about today is that the main requirement they had was that they wanted different levels of users to use the code within the same gateway. To make it a little more, to describe it a little bit more, so their code, the SymVascular code is compiled and it's available in the ECSS resource. Currently they're using Comet. When I said different levels of users, one of the main objectives is to use this gateway in classroom environment for students to use. And their user base would range from undergraduates to graduates, postdocs, and senior researchers. And they also come from not just Stanford, they come from different universities or different organizations. So they want all these users to work within the same gateway. And because of all the users, they also want at a given time multiple exceed allocations to be in use within the same gateway. So other aspect is that since they're working with multiple organizations, they wanted user to not to burden the users with creating accounts, like the manual account creating process in the gateway, but they wanted their organizational credentials to be used in the gateway to get access. The last one, kind of the mainly standing out requirement was that the gateway administrators would be at kind of a different level. So Nathan would kind of oversee at the highest level the gateway activities, but at each group levels, it could be a classroom 1 or classroom at Purdue, like that. For each group level, they would want leads to have oversee the gateway activity. So they they had gateway admins at different levels. So since this is actually an ongoing project, so we are currently working on that. So their requirement, so what we first did was the gateway team is hosting and maintaining the gateway with data storage for the SymSQL application. And for providing access to different levels of users, what the gateway team thought was to have user groups implemented within the gateway. So each user group would have their own set of properties and their own specific allocation, in this case in Comet, to be used. So one group would have different properties defined in the gateway when it comes to working with Comet. To give a little bit of example, a classroom at Purdue would want to only let its users, the group users, to submit jobs only up to maximum of 2 nodes, using 2 nodes. But if it's very senior researchers, they would want to give the maximum nodes that Comet itself provides to submit. So what we thought was we'll introduce groups into the project, so it will have them define their own set of properties in order to submit jobs. And the other thing is, since they wanted the organizational credentials to be used from each organization or university, we had to use the federated authentication system in order to provide this. So currently we are using CI logon for that. So that is actually in production even now. So that is the implementation that we have, and this gateway is kind of in production, and it is being used by classroom environments in different universities. But there are a little bit more to implement when it comes to user groups, and that is what currently the gateway team is working on. So the next I'm going to touch up on a project that has actually been done some time back, but it's also, it brought a different requirement to the table. So I thought I'll briefly discuss about this as well. So this software is it's a joint project between the Computation Research Center at Rensselaer Polytechnic Institute, as well as Colorado Boulder University. So Professor Ken Jensen and also Dr. Cameron Smith are the PIs in this project when we had this. So the thing that what it brought to the table was that, so they needed also a hosted and maintained gateway. And the main requirement here was that they had very long running jobs, which would go beyond the defined maximum wall times of a partition. And that is the main requirement. So they wanted the job to be divided or broken into smaller jobs, so it would, until the job gets completed. And that code is also deployed in Exceed Resource Stampede 2. So the implementation that the gateway team took over on this was similar to all the both gateways before. This gateway is also deployed and hosted for the user, for the PI. And the long running jobs were handled by breaking them into smaller multiple jobs and submitting them one after the other to the Exceed resource from the middleware. So this is also currently a production level gateway, and the tool, the PASTA tool, the software is installed and running and available on Stampede 2. So these are the 3 projects that I wanted to briefly discuss. And
Eroma, can I ask a question? This is Nathan, about when you say long jobs are broken into multiple job submissions.
Yes.
Was that done by your team in some way? Or, for example, did FASTA basically run a certain number of time steps and then write restart files and then restart? I mean, I guess, how was that? Can you just provide a little insight into what you mean by breaking up a long running job into multiple job submissions?
Yeah, so it was breaking it into multiple jobs were done by actually the Apache IRA with the middleware. So we in our system, we know we have defined and we know the wall time limits for each partition of exceed resource. And every time the job runs, the first job runs up to that limit, then it will come back and get back to IRA with the middleware, and then it submits the second broken job. So it's actually done by IRA with the middleware. Did I answer your question?
Well, I don't want to. I mean, to some degree, I'm still confused by it, but I'll let you move on. Maybe I can come back to it during more Q&A if there's time at the end. How's that?
Yeah, sure, Nathan. Even if maybe we can even have a discussion offline as well.
Okay.
So what did we kind of learn, or what did we get to know from all these projects? So it was clear to us that the gateway PIs would prefer the gateway developing team to host and maintain the gateway with data storage, because I understand and we fully agree that they would want to focus on their science and building the community around their code. And they also put a lot of emphasis that the users to feel comfortable about using their gateway. So, and the other thing is that they have all these three gateways use community allocation for their users, and they want to use that allocation sensibly and carefully. And another thing is that a gateway user management system or identity management system is also essential for the gateway. So it would know its user base and who uses and things like that. And for all these gateways, what was the middleware or the gateway provider used? So these gateways are provided with Apache IRA with the middleware. So IRA with the runs computational experiments, and what it does is it encodes how to run wide range of applications, scientific applications, and on wide range of resources like national resources like Exceed and campus resources and cloud resources. And it also takes care of staging files like input files for application and output files of the application to and from the resource. And it monitors all the running application executions and take care of data, metadata generated by these experiments. And so the hosted IRA with the middleware service is known as SciGap platform, and the services from SciGap platform are few is that main ones are the deploying and hosting the gateway and storing experimental data files for each gateway, and it integrated with the middleware. And the SciGap team would take care of regular code and software updates in related to the gateway and the middleware. Another aspect is that once the gateway is deployed, it's not that we would hand it over to the gateway PI for the rest of it, but we would be there, the SciGap team or the gateway team would be there all through the gateway configurations and adding applications and testing before it's available for its users. So once the gateways are in production, the next is to do the community outreach in order to get users on board. So the outreach could be through tutorials, workshops, posters, and papers. And I'm very happy that these gateways that we discussed today, they have ongoing outreach in progress. So for example, PASTA have accepted and submitted poster in last work, and they're doing one this time as well. And DREG has submitted a paper to PERC 18, and Synvascular have their poster accepted and waiting to publish the final for the PERC 18 as well. So we talked about all these gateways that are in production and in good shape, and what insight or what did it give for us in general for the future gateways, or how it helped us to enhance. So one thing is that these gateways, particularly in direct gateway, they wanted gateway code level customizations. So then it got us thinking that we might need to look at a framework that would make gateway level code level customizations easy. And when it comes to SymVascular, it gave us insight on total different levels. We have multiple user groups within the same gateway. The groups, in fact, act like mini gateways within a gateway. So how better we can all provide these. And also these customized developing tools, how to better assist and provide interfaces that suits each of them. So those are things that we started thinking and down in that line. So one thing is that then the gateway team decided that, so currently we have a PHP based framework used for our gateway interface development. So then now we are in process of moving into Django framework because it shows that all these things are kind of easy to do with. And the other aspect that we as the gateway team are developing in order to provide better service and to assist all these gateways in a single platform is to have more robust job submission and monitoring. So we are moving into Helix, that is an open source task execution framework for job submissions. And also we are in place of having multiple job monitoring mechanisms in order to better serve the gateway community. So that's all I have, and I hope I didn't take too much time, and any questions are welcome now.
I had a question. This is Edwin.
Hello?
I have a question.
Yeah, David.
I was wondering, the first of these that you mentioned, they are submitting jobs on Bridges and Comet, you said. And I was wondering, what kind of setup has been used to do so. I mean, we are developing, actually we developed already a functional prototype to do so, but I was wondering, if you had any other, ideas on how that worked for this project and how this was accomplished and, suggestions, right?
Okay, let me try to answer that. So for Comet and Bridges, I believe I mentioned it when I was talking about the direct gateway. So they are particularly submitting to GPU nodes or the GPU partition of Comet and Bridges. So what we do is we do SLURM-based job submissions from Airavata middleware, and which would create a job submission script, and then it would be passed from the middleware into the Comet in order to get executed.
Right. It's about that pass, right? So you're running this on Jetstream, and then this pass needs to be gone into Bridges or Comet. How does this pass?
So the gateway is in Jetstream, and the middleware component that it connects with is in another VM here, another server. No, it's not in Jetstream. So the files are taken from the gateway in Jetstream gateway VM, and they are transferred to a temporary location in the middleware server. And from there, again, it's transferred into Comet. We use SCP for the file transfers.
Okay, so you just use SCP and SSH to do all these. Yeah. Okay, thank you.
I could add, we implemented with JSCH, some Java libraries, so Arvata is all written in Java. So there's some non-trivial considerations for how to do that scalably that I won't get into. But the code's all open source, and you can go to the Arvata dev list or contact us or poke around the code if you want to see some of the things that we do. And then I'll add also other people do other things that might be of interest in a future talk, like the Pulsar approach that Galaxy uses.
So you said you're using this with Avada?
Yes, with Apache Airavata.
So that's the thing is doing this
File
pass part.
Yes, the file transfers. That's a middleware component.
Okay, thanks.
David, I have I can send you the details if you want to poke around and have a look.
Yeah, that would be great. Thanks.
Okay.
So other questions, and maybe, so Eric is next. So Eroma, if you want to stop sharing and
Oh,
let
okay.
Eric get started. And while we're doing, if anyone has any other questions, feel free to ask.
Okay. This is Edwin. I had a question. Can you hear me?
Yeah, go ahead, Edwin.
Oh, okay. So for the DREG Science Gateway, you mentioned that KeyCloak was used for identity and user management. Was KeyCloak integrated with user and accounting systems, and how much effort did it take if it was? And then I guess generally speaking, was there a specific set of features that KeyCloak solved for DREG compared to other authentication systems like perhaps CAS or Shibboleth or maybe even Globus? Should I repeat my question?
Eroma, did you hear that? Oh, maybe they're not hearing you.
They're muted right now.
Oh.
Oh, sorry. This is Marcus Christie. I'm a Theravada developer. I worked on the KeyCloak integration. Would you mind repeating the first part of the question?
Yes. So was KeyCloak integrated with Exceed user and accounting systems? And then how much effort did that take? No?
No, it wasn't. So what we use KeyCloak for is to do the authentication. So KeyCloak makes it fairly easy to plug in other identity providers. Primarily, we use CI Logon, which itself federates to other identity providers. And then we also use it, we do use it for some authorization services. It has a notion of roles that can be assigned to users. So we query KeyCloak to find out what roles a user has and make authorization decisions based upon that.
Oh, okay.
You have a paper about it that we could send a flyer to from Gateways 2017?
Yeah. Yeah, I could send you a paper on the KeyCloak integration.
Oh, that'd be great. Thank you.
Okay.
So I'll mute so Eric can take over.
Okay, sounds good. Let's see, I'm going to share my screen now. Can everyone see my slides?
Yes.
Great, and please let me know if you can't hear me or if I go too fast. Feel free to interrupt and tell me to rewind a little bit. So I'm Eric Coulter, primarily with the Exceed Cyberinfrastructure and Resource Integration team. And I'm going to talk about our work with the Science Gateways group and as an ECSS consultant, building clusters in the Jetstream cloud for people. So this project is kind of an outgrowth of me being split between 3 different groups, which I'm sure many people here are. This all started with work when Jetstream was new with the SGRC to work on a way to expand the SEAGrid gateway to use resources available on Jetstream. And like Eroma said, most of the science gateways expect to have an HPC type resource to submit jobs to. And as I was part of the then called the campus bridging team, going out and helping people build clusters, it was a natural answer to me to take Jetstream and build a standard HPC cluster out of virtual machines, which depending on your perspective may or may not be a good idea. But generally the VM performance is very close to bare metal. So it's worked out as a sort of unusual resource that we've made available. First, I'm going to describe the actual sort of product that we've created through this project, and then talk about some of the actual projects that have production virtual clusters, and describe the process that we go through of actually setting up a new virtual cluster project. So when I talk about a virtual cluster, at least my virtual clusters, the whole plan was to keep it as simple as possible from the beginning. In XCRI, we recently started using the OpenHPC project for our hardware installs that we help people with. And thanks to the fact that it's a very modular project, it actually enabled building Jetstream virtual clusters in a much simpler manner than an initial design that involved actually building things like Torque and SLURM from scratch on a Jetstream VM. The basic design has a single head node with maybe a small size VM, which is capable of automatically spinning elastic compute nodes up and down in response to the job load on the main machine. And I'll get into details of how that works soon. Typically 5 to 10 compute instances, depending on what researchers need. It's very, very easily configurable, thanks to how configurable Jetstream is. The most we've done at once is about 15 large compute nodes for a tutorial, which was fairly straightforward, but we did a lot of testing beforehand to make sure that the whole thing wasn't going to come crashing down mid-lesson. And users, we can provide something like a login node with visualization software as well. We have a project in the works where we're going to be providing that. Users are just managed by standard Linux user management. It would be an option to use an identity provider through LDAP or something like that if a researcher needs extra users. We expect job submission from basically a single user from like an Eroma gateway, or we can allow people to actually log in directly and submit jobs via the command line. The trickiest part is generally customizing these to a particular group's software needs. So recently we had a project that involved installing MATLAB, making MATLAB work in this system. And the MATLAB images in Jetstream were currently on CentOS 6, but all of the actual cluster software is running on Cent 7. And so we ended up building a completely custom, well, slightly customized compute image that could interoperate with the Cent 7 head node. It looks basically like a bog standard simple cluster. The head node is what people actually log into and has a public IP. And then there's the private compute network within Jetstream. It's all pretty straightforward to set up just using the Openstack command line client. It would also be possible to set this up to work using something like Heat, where it's all templated. And I know Miklo has done some work in that direction. So like I said, it's pretty straightforward to set up. I have a Git repository, which I'll share the link to at the end of this. But basically, you create the head node via the OpenStack CLI. So you can't use the Atmosphere client to launch one of these because the head node itself has to be able to manage the elastic compute node. So it has to run on the API side of Jetstream. And And once you have the head node up, we have an install script that's basically bash to install SLURM, create, and set up the Openstack client on the head node to be run automatically to bring compute nodes up and down. And typically people need a lot of storage, so we'll attach a large sender volume on the head node and share it by NFS across all the compute nodes. And we actually have one on the SEAGrid virtual machine that has a Wrangler mount, so people can submit jobs through the SEAGrid gateway and run calculations using data that they've uploaded to Wrangler without having to pass data back and forth between the gateway and the head node. And then once the head node itself is working, the bulk of the work is in testing the compute node spin up and down process, where SLURM is actually running Ansible when node creation is triggered to install software on compute nodes that are built from a vanilla CentOS image in Jetstream. And luckily, most of the tricky bits of the elasticity are actually built into recent versions of SLURM. So all of the logic that looks at the job queue and keeps track of what when more nodes are needed is part of SLURM, though it's sparsely documented right now. But SLURM has a feature where you can define your own programs to resume and suspend cloud nodes of any sort. So for whatever cloud provider, you can write your own suspend resume scripts. And so when a user comes in and the queue is full because you've got all of your currently existing instances up, you can actually create a completely new compute instance as needed if you've configured that as an option in the total number of nodes. The setup for it is for SLURM to handle this is very small. So this is all that's needed in the SLURM configuration file to start this running. And a very nice piece about this is that it transfers to hardware. So if you have a local campus cluster and a Jetstream allocation, you can actually burst out your jobs on your current cluster to run on Jetstream in a separate queue. And I haven't had a customer to try this out with yet, but it's something I've tried at the level of launching nodes from a different virtual cluster on another one, and it's a pretty cool capability that I'd like to see implemented somewhere. So like I said, we've had 3 production virtual clusters so far. The original one with SEAGrid, working with Sudhakar, is primarily for material science work, largely using Quantum Espresso on this VC, although we're working on adding a larger variety of software soon. And that's actually the one with the Wrangler mount, which is, now that we've implemented it there, we can do it somewhere else as well, but we haven't had a project that required it yet. And then the UltraScan project with Borries at UT Health is running their own custom software on about 10 nodes, and they were the project that had a large workshop that needed 15 nodes for their peak set of calculations, and that's actually a very customized cluster because their software is built in the lab, and so they have to log in and compile it, and then we can test that it's working on all of our compute nodes. And then the Neuroscience Gateway at SDSC is using MATLAB and FreeSurfer that I mentioned earlier. So that's another very highly customized virtual cluster compared to my the basic vanilla image that gets you up and running. And so far, researchers the people we've worked with have really appreciated this sort of extendable cyber infrastructure. The biggest issue we face in setting these up with researcher desires is that someone will come and say, hey, we want 20 large nodes with 44 cores each, and that's just not feasible on Jetstream as heavily as it's used right now, and as given the average size of allocations it would burn through very quickly. It's not the main point of Jetstream to provide resources like this, but it is extremely useful being able to have a fully customized compute resource where your group is the only one on the queue. So the only reason that jobs really wait in a queue is if they're running a lot at once or if something is wrong. And like we said, it's been really useful in workshops. We've run several XCRI workshops using this as a sort of HPC education tool.
Hey, Eric, this is
Mhm.
Marlon. Jump in.
Hey, Marlon.
We have a question on chat.
Oh, sorry about that. So data transfer. So the question is, how would data transfer be handled with bursting to Jetstream via SLURM? And I assume you're asking about in the hardware case, because in the case of a gateway, it would be handled by, at least what we've worked with, it would be handled by Aravata, actually putting the data on the node or mounting to Wrangler. In the case of hardware, it would have to be, at least for now, it would have to be built into the job submission script, which would be kind of a pain for a lot of different types of work. Let's see.
Yeah, so if it is mounted, somehow it can reach one of those, Wrangler mounts, then it is just pointing to the right, path.
Yeah.
Between, I think, the main node and the burst nodes, there is a shared, data system that can be used, that is common to all these things where the data can be accessed. Hope that answers some of those questions.
Yeah, did that help? Or you can always come back to this in question time too. Let's see. Okay, great. Let's see. And all right. And the fact that we can make these elastic really lets researchers maximize the use of their allocation, so they don't have nodes that are constantly running and burning SUs when they're not actually running a job. And so typically these happen so far by someone getting in touch with the SGRC or the SGRC getting in touch with someone and asking if this would be helpful. There's typically a requirements gathering phase of figuring out if this is the right answer for somebody. Just because I think this is a cool thing doesn't mean everyone needs one, right? And currently the build process looks like adding me to the allocation, and then I'll set up the basic virtual cluster and work with the researchers to make sure their particular software is working as expected. And once we hit that point, it's fairly hands-off. And it's at this point in the project, it's a pretty quick process, a relatively quick process. The initial plain vanilla build can be done in about 20 minutes if you don't want any features. But getting everything set up is usually a matter of a couple of days, depending on how many other projects are going on at the same time. And then there's usually a couple of weeks to a month period of testing the actual software and making sure that nodes are coming up and down smoothly. The only ongoing issue is once one of these is up is sustainability. It's not 100% set and forget because these things are full virtual machines. OS updates have to be applied. Occasionally something will happen where one of the instances isn't communicating with the other ones or something. It's pretty rare for Jetstream to have issues, but it does happen occasionally. The thing that happens most is that SLURM gets confused because nodes are coming up and down and maybe jobs fail and it thinks it's lost communication with the node and it really just needs a reboot. Those are typically easy to fix, but it still requires support from our end. And it is fairly easy to figure out what's going on, but not many labs already have people available that can just go into an HPC system and diagnose. Luckily, the fact that you're burning compute nodes down regularly means that if something happens, just burn it down completely and rebuild, and you're back up and running. So if anyone has questions, you can email us at help@exceed.org or exceedcb@iu, or you can just Slack me in one of the many varied Slack spaces associated. And if anyone wants to see code, I've got it online on GitHub. Does anyone have questions, comments?
Eric, I do have a question. You mentioned that there is a capability for projects who are interested who have their own cluster to burst out onto, say, one of Exceed's resources, maybe Comet or Stampede2. Is that correct?
So what I meant that if someone has their own local hardware system, it's possible to burst from there into Jetstream. We haven't set up bursting anywhere else from one of these virtual clusters to somewhere else. Does that make sense?
Okay, to Jetstream. So is going somewhere else possible or not technically possible?
I think that is best handled through a gateway itself. It's not something that's really appropriate for this particular product.
Okay, thank you.
Eric, can you summarize a little bit when you construct the virtual cluster, what's the use of those tools like Openstack client command or Ansible in dealing with the networking part?
Absolutely, yeah. So I guess I kind of skimmed over the actual where all the actual pieces are working. So the OpenStack, can you guys see my pointer on my screen?
Yes.
Ooh, here we go. All right. So the OpenStack CLI is used first to begin with as a script that I have set up to just build the head node, create the router and your public IP address, and provision the private network all in your allocation. And at that point, once this is all set up using OpenStack, then I start pulling in OpenHPC pieces for setting up SLURM on the head node, and I guess it's primarily getting SLURM installed and set up easily on the head node because building it is a pain. and it comes with nice default configuration files. At that point, then SLURM runs scripts itself to trigger OpenStack commands to build the compute nodes as needed. And I typically build compute nodes and then suspend them so that between the actual instance, there's a difference between actually creating an instance and suspending and resuming one. So it takes a lot longer to initially build than to suspend, resume. And I'll usually set it up so that the instances exist but are suspended and not burning SUs, but still start up quickly before a researcher actually gets on the system. And during the initial compute node build, SLURM is running an Ansible playbook to provide the necessary software to the compute nodes. Did that help, or did I confuse things even more?
Router head nodes, they are all virtual machines.
Mm-hmm.
Can they be containers?
So you could build, it could make sense to build a container that would run everything on the head node. You could have a container with the SLURM control daemon and Ansible. I'm not sure. I'm not entirely sure what that would gain you.
For example, if you can use Docker Spawner to manage a bunch of virtual machines, and your container is a customized template for a particular software environment, then you can switch to different containers using the same virtual machine setup.
Mm-hmm. True. Oh, so one of the things that we do get from using OpenHPC is that it's very easy to set up Singularity on here. So you can actually run jobs using a container of your particular scientific software inside of this VC. If you need to run a container, a software that's available as a container.
So does that mean that these compute nodes are still virtual machines, but SLURM just submits the Singularity container instances to those virtual machines?
Yeah, exactly.
Okay. And again, the networking part, does Ansible or any other tools can automate the setup of the network?
Oh, so the network is automated with using in the scripts that I have that use the OpenStack API.
So Ansible doesn't manage that?
No, Ansible only touches the compute node configuration. So making sure that they have software and that they're mounting the shared file system, that they have all of the users exist on the head node, things like that, or exist from the head node.
Okay, so you mentioned OpenHPC. Does that software stack provide a network management?
No, I'm not pulling any network tools from OpenHPC.
Okay, so it's easier to just write own scripts.
Yeah, it just for creating the network. What kind of network management are you interested in?
It just to provide the flexibility of adding a compute node, remove a node without worrying about the actual overload of configuring the network.
I see. So that's all handled very smoothly by OpenStack. when you fire up a new compute node, all of the provisioning to the network is handled through the API, and SLURM is able to detect that new IP address whenever it changes. It's all of that part is pretty smooth.
I see. So if the compute nodes are containers, do you know any of the tools available to manage the network?
If you were using containers as compute nodes, I'm not sure. I know like Flannel and Weave are used for handling container networking, but I'm not. I haven't tried that on Jetstream yet.
Okay, thank you.
Mm-hmm.
Yeah, so Eric, is it fair to say you were really targeting more traditional MPI applications and things like that? So there's lots of other things out there like Docker Swarm and Kubernetes and whatever that are better suited for containers.
Yeah, that's true. This really is aimed more at MPI style workloads.
Yeah, so the UltraScan demo, for example, or the tutorial, that was 24 core nodes where each job the performance kind of maxed out at 24 cores. So that's, but the MPI jobs perform best at 24 cores. So that's how that one happened. So that's sort of a sweet spot maybe for what Eric is working on. Other questions? Okay, well, I'd like to thank our speakers and thank you all for your time and for all the questions.